Now we have another important relationship between logic variables, which is called the DeMorgan's theorem, and which states that if we have three variables A, B, and C, which have been connected to an OR operation, the DeMorgan's theorem states that A or B or C bar, we have said that the prime means the same thing as bar, or they can be represented as such. This can be equivalent to A bar dot B bar dot C bar. This is a very important theorem that we observe, and we normally use an analogy that says break the line and change the sign. What are we seeing here? We are breaking the line. We are bringing the line at this point, and at this point when there is this sign, and we are changing the sign from being a plus to being a dot. So assume we had this continuous. What we did is that when we broke that line, we changed the sign combining the two to become from a plus to a dot. Similarly here, from a plus to a dot. That is the analogy we normally use. We say break the line, change the sign, or join the line and do the same, change the sign. So if we join the line here, they had broken. So what we'll do, we'll change the sign here. Join the line, change the sign. So this becomes equivalent to what we had before. A or B or C bar. But when you break the line, you have broken this line. You have A bar dot B bar dot C bar. That is normally called the DeMorgan's theorem. So DeMorgan's theorem holds for two variables and can be extended for more than three variables. And as you have seen, we have worked with three variables here. It also holds for two variables. For instance, we have A or B bar. This is equivalent to A bar dot B bar. On the other hand, if you have A dot B bar, you can break the line and change the sign to represent A bar or B bar. So it applies on both sides. If the initial dot was dot, then after you have broken the line, you end up with a plus representing OR operation. And we have an example here we want to look at just to illustrate how this can be used. And we want to say that we are given these operations, we want to do a simplification. So what we normally do in such a case is we remember the eight laws of Boolean algebra that we remember. We also combine with DeMorgan's theorem for us to be able to solve this one. So for instance, we know that this one is equivalent to A or B bar. Remember I said prime represents bar. So those are the two ways in which we can express the inversion or the inverter. And therefore, when you see me remove this one prime, this allows me to work with the line that I can break or join. So we have a dot. Whenever you find a missing connector, it means there is a dot operation that is happening there. So we have a dot there and A or B bar or A B bar C. So the first thing that I can do is to break this line and change the sign so that I will end up with this becomes A bar dot B bar, and therefore I can open this bracket using, here I'm using this one, these 8 rows plus the DeMorgan's theorem plus the commutative, distributive and associative flows. What we know is that A or B to bracket AB, you can open that bracket to have to end up with this becomes A or B to bracket. I think I can also open this thing up for the sake of simplicity. A or B bar, close the bracket, or A B bar C. So one of the things to observe here, and I can put a star, is that always avoid working with a bar that is combining more than 2 variables. The easiest way to make things work is that work with bars that have only one variable. Whenever it combines 2 variables, then it becomes very difficult to work with it. So always try to achieve, whenever you're working with DeMorgan's theorem, always try to work with bars that are combining only one variable. That is why I have tried to break these 2 lines so that you can see they are combining A and B. We try to break that apart. They are combining these two. You try to break that apart. So what do we end up with? We have A bar after you have opened that bracket, plus, actually it becomes like that, A times this one, so it becomes A bar dot B bar plus B A bar dot B bar, and this you can open up again. You can still restore that bracket there so that we see what happens after we have simplified the first bracket. What we know is that from our 8 laws of algebra, whenever we have A dot A bar, remember, you see this is always equals to 0, and for that reason this term goes to 0. Similarly, we have B dot B bar, again this is always equals to 0, so again this term becomes 0. I just noticed a correction here that we need to do. Here was A or B, but this was a C. So this is where I am seeing an error there. So this is a C, this is a C bar, and this is a C, this A times this, and this is a B times this times C. So this is a C. That is a correction I have just figured out, that I may have made that error. So what will not go to 0 is this one. So clearly this is not a 0. So when this goes to 0, then we are left with B A bar C bar, then other. So we will have A bar. Remember, A bar dot A bar is the same as A bar. So we will have only one A bar, B, this B, and C bar, plus, let's open this bracket. Now this dot that will form this part, because as you can see, we have B dot B bar, this becomes 0. So this term goes to 0. Let's see what we have here. A bar and A bar. So A bar and A, again, this term goes to 0 because we have this A dot A bar. So we are left with this as the final answer, or plus 0 becomes A bar B C bar. So this is your final answer of Y after you have done the simplification. So we do another example that says simplify the following using the following Boolean expression. So what you also notice that you never be told use the DeMorgan's theorem to solve. It is you to know if you are finding yourself to solve such an expression, you can use the DeMorgan's theorem in addition to DeMorgan's theorem. That is 1. You use the 8 laws of Boolean algebra, and number 3, you use the commutative, distributive, and associative laws of Boolean algebra. And one of the most useful in this one is the DeMorgan's theorem. So what we know in this case is that we have A, C, D bar plus B, C, B into C plus A, B, D bar. You can see you have this apostrophe up outside the bracket. Then into bracket, this bar means that all of these are bad. Again, you say that again up to this B where the bracket is, there is another bar right there, plus A bar B C bar D bar. So we say that we want to work with bars that are only connecting with only one variable. The first one we'll simplify is the first one, becomes A bar plus C bar plus D bar. Again, we open this bracket up. You start with the most inner one. So what we will have here, we have B bar plus D bar into bracket A plus C. Now I'm going backwards so that I can remove this bar because it's working on all of those. And when we have that, we will have equivalent to C bar dot A when we broke this bracket, or this now becomes all B bar plus D bar on top. Again, when we break this up, it will become dot, and this will become 2 bars. So whenever you have 2 bars, they are equivalent to no bars at all. So we have, I remove these 2 bars. So what we have now is we have C bar dot A bar, this has an A and a bar, or B dot D. So we now need to introduce this one that is outside. Get a bracket here, and we had a B which was barred. When we break this bar, we will be left with this bar plus this had a bar, which when we break, this will become, break this line, we break this sign, change that sign, break this line, change this sign, break this line, change that sign. So what do we have? We have B bar, or C bar bar becomes C, A bar bar becomes A, dot B bar, that bar, or this became a plus, D bar, you can introduce your brackets there. So what are we finding here? The final answer should be, these have not changed at all, plus these other ones. So I'm writing my solution here as A bar, this one, plus C bar, plus D bar, plus now this, B bar, plus C bar, and I open the bracket, plus A dot B bar, A B bar, plus A D bar, plus this one now, A bar, B, C bar, D bar. So again here I see a very simple mistake. We have said that this is C without bar, but when I was transferring it here, I brought it as C bar, because we have said these three are these three. Then we have B bar, this one, and we have C without a bar, so this is without a bar, and then we have A B bar, this is B bar, and A D bar. So what we now find after that, what we now find is that we have this relationship, this or this. You remember we said A or A bar is equals to a 1, and therefore because we have C bar or C, then clearly this becomes a 1, and therefore we have the final answer as equals to 1, this one, or everything else. Call it M. But you also remember that 1 or M is equals to 1. Therefore, the final answer for this solution is equivalent to a 1. So, well, no matter how other method you use, whenever you solve all this, it will give you the answer as 1.